Hello, in this video we're going to talk about rockets. So we've got our rocket here, and I'll draw kind of a cartoony rocket just because I can't draw a real rocket without it looking weird. So a rocket has mass m and velocity v, and then some time later a rocket will have changed because it will have ejected some amount of exhaust. Typically this is going to be particularly hot gas being shot out of the rocket. We're now moving at a slightly higher velocity because we're throwing mass out the back. We'll show that that's a consequence of conserving momentum. Our rocket has lost a little bit of mass because that extra mass was shot out as the exhaust, and the exhaust is moving with its own velocity. We'll call it u because we've already used up v for the rocket. Now let's be careful with how we define our system. Remember, the definition of our system has very important implications for when we try and set up conservation of momentum. So if we look at our initial case, clearly the system is the rocket. What about after it's shot out some exhaust? Is my system still just the rocket, or is it the rocket and the exhaust? Well, it has to be the same stuff. Conservation of momentum doesn't work if mass has entered or left the system. We don't want this to leave the system, so we need to make our system bigger. So our system is the rocket and anything that was once inside the rocket. Now we're going to do all of this from the point of view of some stationary observer. So here we have some floating eyeball looking upwards. We don't even actually have to be stationary, but we do have to be inertial, meaning our observer can't be accelerating. So they need to be sitting still or moving at constant speed. All right. And one more setup. The difference between the initial state and the final state is a small amount of time dt has passed. All right, so let's talk about the exhaust. The exhaust is going to move at speed v exhaust relative to the rocket. This u here is a speed relative to the observer. And so in fact, depending on how fast the rocket's going when it shoots out the exhaust relative to the observer might actually be moving to the right. So v exhaust and u are not the same velocity. They are from different points of view. The relationship between the two is that v exhaust is equal to the speed of the rocket plus u. Now keep in mind u is in the other direction, which is why we're not putting in a minus sign here. Also, I want to point out that in this derivation I'm going to use different sign conventions than the textbook does because I think they are more consistent. If you read the textbook, you'll get a different version of the same derivation. Just keep in mind that they might use pluses where I use minuses and vice versa. Okay, now anyway, the reason we define this is that it's a helpful quantity because this number is constant. The speed of the exhaust relative to the rocket has nothing to do with how fast the rocket is going. The speed of the exhaust with respect to the observer does depend on how fast the rocket is going, and so it's not constant. In any case, from our observer's point of view, actually from anybody's point of view, as long as they're in an inertial frame, momentum is conserved. And so that's how we can approach this problem. What we're going to do is we're going to calculate what the force is on this rocket thanks to its exhaust, which is what you'd want to know to eventually figure out how fast does the rocket go. Now it might be tempting to try and use the momentum impulse theorem. So it might be tempting to say that, and let's put this in a different color, to say that delta p is equal to j is equal to the integral f dt, and therefore f must be equal to dp dt, and just integrate p. No, you can't do that. You're not going to get the right answer. So this is not a case where we can use Newton's second law, f equals dp dt, because this was only true when the mass was constant. The mass is not constant. Our rocket is losing mass. However, we can still say that momentum is conserved. We can still say that delta P equals 0 because we've defined our system to include both the rocket and its exhaust. So that will still work. So P initial is equal to P final, and P initial is equal to M times V. And P final has two pieces to it because we have the rocket and its exhaust. The rocket has momentum m minus dm times velocity v plus dv, and the exhaust has mass dm and velocity u. U is to the left as I've defined it here, so actually we want to put in a minus sign. Minus sign because u is drawn to the left. So let's multiply out this right-hand side. So we'd have m times v plus m times dv minus dm times v minus dm dv minus dm times u from our last term. So we can cancel out mv, and it might look like we have kind of a mess over here. So actually, what we can do is use this statement earlier that v exhaust is v plus dv plus u. Let's look at terms that have u's in them. So this one has a u in it, and it's got a dm. Here's a dv with a dm. Here's a v with dm. So actually, this is exactly what we need. We can rewrite that term. We'll rewrite the whole equation as 0 is equal to that 0 plus m dv minus dm times v plus dv plus u. All right, and so this, running out of slide, I realize, this is equal to negative dm times v exhaust. Okay, so let's rewrite that on the next slide. So I'm just restating the very same equation. 0 is equal to mdv minus dm times v exhaust. This kind of looks like a product rule, although you have to be careful with how you define v exhaust. So you can't just quite jump straight here. It's tempting to, but it doesn't really work out. Anyway, let's clean this up a little bit. We'll put v exhaust dm on one side of my equal sign. I'll put m dv on the others, and I'll call this equation 1 because I'm going to use it a few times. First thing I'm going to do with it is I'm going to divide equation 1 by dt. On the left hand side I'd get v exhaust times dm dt, and on the right hand side I get m times dv dt. I've actually made derivatives. This is called implicit differentiation. When you take a statement with differentials and divide it by a different differential, that's equivalent to differentiating. And on the right hand side, this is ma, force times acceleration, or mass times acceleration is a force. We're going to call that force thrust. Okay, and we'll use the symbol T for thrust. So this statement is simply that the thrust is equal to the exhaust velocity times the rate that the mass of the rocket is changing. In other words, how quickly it uses up its fuel. That's what we wanted to do. We wanted to find out what the force on the rocket was. This is called the first rocket equation. As you might guess, in just a moment we're going to derive the second rocket equation. And this term here is the interesting thing. It's the rate that the fuel is used. The faster the rocket uses its fuel in terms of mass, the more thrust on our rocket. So actually an interesting bit of rocket history. This was early in the rocket program. Some people from NASA were trying to calculate what's the most efficient rocket fuel. Something that has a lot of mass and burns really well. Something that burns really well will have a large exhaust velocity. Something with a lot of mass will make this term very large. And they decided that the best rocket fuel would be dimethyl mercury. If you're not familiar with dimethyl mercury, it is one of the most ridiculously toxic materials that is out there. In the late 90s, a researcher got just a few drops of it on her gloves, not even on her hands, on her gloves, and then she died because it's so incredibly toxic. So anyway, they called up Kodak, who at the time was a big, not just photographic company, but also general chemical company. Called them up and said, hey, we want 100 pounds of dimethylmercury. And they were then politely told that that was a horrible idea, and no thank you, no way would we make that. Not only is it going to kill everyone in our plant if we tried to make that much dimethylmercury, it would also ruin all of our film. So, nonetheless, they don't use that for rocket fuel. Okay, back on topic. Let's come back to equation 1. Another thing we could do with equation 1 is we could integrate it. Let's just do that on the next slide. So we can also integrate equation 1. So we had V exhaust times dm is equal to m dv. Let's move this m to the other side so it matches up with the dm. So on the left, we'd have V exhaust is equal to dm on m, or V exhaust times dm on m is equal to dv. We then want to integrate both sides. V exhaust was a constant. Remember, that's why we defined it, so that it could be a constant. So that comes outside the integral. And we only had one term on the right to integrate. And when you do this, when you integrate both sides of an equation, the limits have to be consistent. So, for example, on the left-hand side, we go from the initial mass of our rocket to the final mass, which is generally going to be less mass. The mass is going to be decreasing. And on the right-hand side, we have some initial velocity when we have the initial mass, and then we have a final velocity when we have the final mass. So let's carry out the integral. On the left-hand side, we have V exhaust times the natural log, that didn't come out right, times the natural log of the final mass minus the natural log of the initial mass. And on the right-hand side, we have the final velocity minus the initial velocity, which we could write simply as delta V. It tells us how the velocity of our rocket changes. There's also a nice trick we can use to clean up the left-hand side, a property of logarithms. The log and the natural log of A minus the natural log of B is equal to the natural log of A divided by B. So the left-hand side of our equation becomes, let's actually just write it backwards. So delta V is equal to V exhaust times the natural log m final on m initial. And that is the second rocket equation. It's not really giving us any information that wasn't in the first, because they really are, they come from the same starting point. But it's a different way of stating what happens. Instead of what's the force on our rocket, how much does our rocket's velocity change? And in many cases, that's actually what you really want to know, is how fast can I make my rocket go? Can it go fast enough to get to space? Or is it not going to go to space today? Well, to figure that out, you need to know the exhaust velocity of your fuel, higher is better, and how much fuel you use up. This is going to be a positive number because the final amount of fuel is, or the final mass of the rocket is going to be less than the initial mass of the rocket. And this is total mass of the rocket. So let's say our rocket is half fuel, then the final mass is a half. The initial mass would be 1, would be the natural log of a half. Is really not that impressive. This statement here is, this is why rockets are mostly fuel. Think about a rocket. It's basically just a big fuel tank made of as light a material as you can, with almost all of the interior being fuel that you use up. And one way you can kind of help this is as your rocket uses up each stage. So we have our fuel tank separated into pieces. As each each stage runs out of fuel, you drop it off. And so now you have less mass, which means you get to go faster. And then when this one runs out, you drop it off. And then this one, you drop it off. The name of the game is to throw away as much of your rocket as possible, to go as fast as possible. It's, of course, very, very inefficient from a materials point of view, but necessary. The physics just says that's how it has to work. All right, well, that will do it for this chapter. So I'll see you next time, where we're going to start to talk about not just linear motion, but rotational motion, although we will also merge it in with linear motion. We'll be building on what we've done here. So I'll see you then.